this session, I would like to discuss the various aspects related to a GIS database. GIS data are collected from various sources. A large portion of these data is managed in databases. The database approach provides a robust method to data organization and processing in the computer. However, it is also requires more effort and resources to implement, and therefore, the design and building of GIS databases is an elaborate process by necessity. Databases offer more than just a method of handling the attributes of spatial entities. They can help to convert data into information with a value. Information results from the analysis or organization of data, and in a database, data can be ordered, reordered, summarized and combined to provide information. A database can perform sorting, ordering, conversion, calculation such as the maximum and minimum value, the average, etc., and summary. With the additional mapping capabilities of GIS, the location of points with a particular information can be mapped. For making decisions, the GIS needs information derived from the stored data in database. So, what is a GIS database? It is a collection of multiple files made up of three basic types of the structure for data storage, retrieval and organization of data. There can be three ways of storing the data in a database. First is simple list, ordered sequential files and indexed files. So, let us look at them one by one. Simple lists. The simplest form of database is a simple list of all the items in which any new item, when added to the database, it is simply placed at the end of the file. In such files, it is easier to add data, but retrieving is not efficient, and for this reason, in a large data set, searching a particular item takes long time. Supposing a list consists of n data items, then searching a single item, the computer requires on an average of n divided by 2 operations. If a computer takes 1 second to read a card having certain information, to search for a particular information from a pack of say 200,000 cards, the computer has to perform as many as 200,000 plus 1 divided by 2 search operations, which requires more than 27 hours. It obviously shows the need of an organized database. The next type of file is ordered sequential files. In ordered sequential files, the data items can be arranged in an alphabetical order as in a telephone directory. The normal strategy for search is based on divide and conquer approach. Instead of beginning the search at the beginning of the file, the record in the middle is examined first. If the desired values do not match, the search proceeds to find out whether the required item occurs before or after the middle element. the appropriate half of the file is retained and the search is repeated until the item has been located. Very often, ordered sequential files are accessed by a binary search approach. A binary search requires log to the base 2 n plus 1 steps. So, a file containing 200,000 data items will require nearly 2 hours to compare to 27 hours in simple list, assuming each operation takes 1 second to perform. In ordered sequential files, whenever a new item is added, an extra space for it is created before inserting it, but the advantage is that the stored item can be searched faster. Next type of files is index files. In geographical information, the individual items such as points, lines or areas carry information about the associated attributes in addition to a identification number or name of the key attribute. Typically, a search will consist of finding the entities that match a selected set of attribute criteria. In most cases, a large number of attributes are linked to an entity. A more efficient method of search is required to find out specific entities with associated cross-reference attributes. This requires another database strategy of search procedure. In the index files, we can have another procedure of data storage in the form of direct files. So, this is one of the ways of speeding up the access to the original file data, which is an index file. If the data items in the files themselves provide the main order of the file, then these files are known as direct files. The table below shows a simple structure of a data direct file, wherein in the index we have the item key and the record, and corresponding to that it has the file item. So, item key A, which is located at record number 1, corresponding file item is A1. For item number B, which is located at a record n plus 1, this is having a file item of A2 and so on. So, in this manner the files are being provided certain correlation amongst themselves. Another way of expressing locating items in the main file may be by specifying the location according to topic given in the second file, known as an inverted file, as shown in this particular table below. So, here what we have is soil profiles of a data of a soil profile, and corresponding to that certain attributes have been provided. These attributes have been categorized as the soil grade, the drainage pattern, the depth of the soil, the acidity and the erodible rate. So, for soil profile 1, the informations have now been provided as A, good, deep, 5 and Y, which means certain attributes of the soil profile has been stored. Similarly, for different soil profiles, the information again has been categorized and the data has been saved in an inverted file. Now, what we can do is, we can now carry out a search procedure to locate a particular property by arranging the data file. So, what we can do is, Now, we can select the property and we can say identify those soil profiles which have good drainage. So, then what it will do is it will identify profile number 1, 2 and 5 from the original data to be having good drainage. So, naturally, the other two profiles 3 and 4 will be attributed as poor drainage. Similarly, depending upon the depth, we can say the profiles 1 and 2 have deep depth of soil, whereas 3, 4 and 5 will naturally be shallow. Similarly, we can find out whether the soil is consisting of, whether it has the potential of erosion or not. So, what we can do is we can now search the file and find out all soils which have erosion capabilities or prepared or which have been generated from eroded material. These are 1 and 5 and so on. Though the index files permit rapid access to the database, they have inherent problems when used with files in which records are continuously being updated by adding or deleting the records, such as in an interactive mapping system. Updating of records in direct files requires that both the file and its index must be modified. When new records are written to a file accessed by an inverted file index, the new record does not have to be placed at a special position. The new record may be simply added to the end of the file, but the index must be updated. File modification may be an expensive affair when dealing with large data files, particularly in an interactive environment. Another disadvantage of index files is that very often data can be accessed through the key containing the index files. Other information may be retrievable using sequential search methods. Having had a look at the file systems by virtue of which the data can be retrieved or looked at, now let us look at the database management system which will store these files. A DBMS is a computer program that is designed to store and manage large amounts of data. The overall objective of a DBMS is to allow users to deal with data without needing to know how the data are physically stored and structured in the computer. A DBMS must allow the definition of data and their attributes and relationships, as well as providing security and an interface between the end users and their applications and the data themselves. The functions of a DBMS can be summarized as: first, file handling and file management, adding, updating and deleting records, information extraction from data, maintenance of data security and integrity, and finally, application building. In order to provide a structured approach to the organization of data files within a DBMS, there are three fundamental ways of organizing information that also reflect the logical models used to model real world structures as below: hierarchical database structure, network based database structure and relational database structure. The object oriented database structure is an emerging trend in GIS and a topic of current research. Of these four databases, the relational database structure is most widely used. So, now let us look at each of these database structures one by one. First is the hierarchical database structure. A data may have multi-layer data with direct relationship with each other, similar to a tree-like structure. Let us look here at a very simple example to illustrate hierarchical data structure. There are two polygons having corner points A, D, C, B and D, F, E, C, with C and D points being common to both the polygons. So, we can now represent the whole figure as M, that is the map, and this map consists of two polygons, polygon number 1 comprising of the points A, D, C, B and polygon number 2 comprising of the points D, F, E, C. So, the two polygons, there are two polygons. So, what we can do is we can show two branches from the map, one to show the polygon 1 and the other to show the polygon number 2. Now, the polygon each of these polygons will be consisting of a number of sides. In this example, since it is a regular square that we have taken, so let the lengths of the lines be designated as L1, L2, L3, L4. Similarly, for the polygon 2, the lines which enclose or form this particular polygon are L5, L6, L7 and L3. Now, these lines have end nodes. So, what we can do is for the lines, now we can say that each of the lines which are the points which connect them. So, these could be for line 1 it is A and B, for line 2 it is B and C, for line 3 it is C and D, for line 4 it is D and A. Similarly, when we consider the second polygon 2, we find that the line, it consists of lines 5, 6, 7 and 3, wherein line 5 has end nodes as C and E, line 6 has end nodes E and F, line 7 has end nodes F and D, while line 3 has end nodes D and C. The relationship between the two layers is known as a parent to child or one to many relationships. In such type of data, hierarchical databases provide a quick and convenient means of data access. Here, each part of the hierarchy can be reached using a key or criterion, and there is a good correlation between the key and the associated attributes. So, let us look at the advantages and disadvantages of hierarchical data. The main advantage of hierarchical database is that it is simple and provides easy access through keys defining the hierarchy. Further, it is easy to expand by adding more attribute and formulating new decision rules. The success of data retrieval in a hierarchical database depends upon the prior knowledge of the structure of all possible queries. One of the biggest disadvantages of hierarchical database is the repetitive data. Referring to the figure discussed earlier, it can be seen that each pair of points is repeated twice, and that for line 3, the coordinates C and D are repeated 4 times. This is a simple wastage and causes large redundancy of data in case of large databases. In hierarchical structures, the access within the database is restricted up to the paths up and down the hierarchy levels. Then we come to the next type of data structure, which is networked. Many a times a single entity may have many attributes and each attribute is linked to many entities. To accommodate these relationships, each piece of data can be associated with an explicit computer structure called pointer, which directs it to all the other pieces of data to which it relates. Rather than being restricted to a branching tree structure, each individual data is linked without the existence of a parent to child relationship. Such a data structure is called the network data structures. The figure below takes up the same example of a map consisting of two polygons, and now what we can find is that there is a very simple structure which has been created by providing pointers. So, what we can see is that line 1, it is linked to points A and B. Similarly, what we can see is that point B is linked to line 2. In the same manner, line 2 is linked to line C and line C is linked to line 3. Now, interesting part is that when we come to point D, we find that it is linked to line 4, it is linked to line 3, it is linked to line 7, which tells us that here we have now saved a significant amount of data repetitivity by providing only one single value of D, but providing its linkages to the various entities to which it is correlated. Well, sometimes what we can do is, in order to reduce both redundancy and linkages, a compact network structure known as ring point structures can be used so that each entity appears once. Taking the same example, in this figure, each point is having different linkages or points. The figure shows the ring structure where the flow has been simplified. That is, that now polygon 1 is like a sort of a ring consisting of the lengths L1, L2, L3, L4, and that when it loops back, it completes the polygon 1. Similarly, the polygon 2, what it shows is that it has the lines L5, L6, L7, L3, which is connected to polygon 1, and again from there it comes back to the end of polygon 2. So, in this manner what we find is that once we are into one polygon, we know what could be the path. Network structures are useful when the relations or linkages are specified beforehand. They avoid data redundancy and make good use of available data. Hence, they allow greater flexibility of search than hierarchical data structures. The disadvantage of network structure is that for large databases, the number of pointers can become large and can become a substantial part of the database. Further, these pointers have to be maintained every time a change to the database has been made. Building and maintenance of pointer structures may be a considerable overhead for the database system. Next is relational database structure. In relational database structure, data are organized in a series of two-dimensional tables, each of which contains record for one entity. These tables are linked by common data known as key. It is possible to make query on individual or a group of tables. In this particular slide, the relational data structure approach has been illustrated. So, it is a file related to land title, wherein it has various attributes, that is what is the land number, what is its area ID, the date when this land was purchased by a owner, and its location. Now, what we can do is we can further categorize the information for each of the land title, wherein we can introduce attributes regarding what is the category under which this particular land is there, or what is the registration number. So, these are specific to each parcel or land, and thus what we call it, we create a parcel table, which is nothing but another attribute set, wherein for each of the land IDs, these information regarding the size of the parcel, the category under which it falls in terms of the size, and the category registration number. Now, we can further create another table, which we call it as the ownership table, that is, who is the owner, wherein the details of the owner would be provided. So, this would be again linked by the land ID, and thus for each land ID there would be the name of the owner, what is his postal address, and other information like telephone number, etc. So, here what we find is that the information has been created in separate files, and certain relationships between the file through a key has been generated, and that particular key is the land ID. Based on that, the subsequent process of acquiring the information has been made. So, what we can say is that each table contains data for one entity. In the first table, the entity is land title. In the second and third tables, the entity is parcel and owner. The data are organized into rows and columns, with columns containing the attribute of the entity. Each column has a distinctive name, and here every entry is a single column, must be drawn from the same domain. Another example is of a utility consumer management, wherein the informations could be in the form of district. Within the district, what type of service is being provided and who could be the possible users. So, each user has an ID corresponding to individual users, the information regarding the name, address, consumer type, the amount that he probably spends on particular type of services, they could be entered. Now, this address can also be used as a key, wherein the information could be that depending on the type of the typical address, we can find out what type of consumer he is, what is the name of the owner, and what could be the user ID. All these informations could be there, and these could be linked to the database. Some of the disadvantages of relational database are that it cannot handle geographical concepts such as connected to, near to, or far from. It always produces some data redundancy and can be slow and difficult to implement. It is difficult to handle complex objects such as found in GIS, as there is a limitation on the range of data types, difficulties with the handling of time. Another database which has now been the focus of attention is object oriented database structure. Object oriented concepts have its origin from computer programming languages and have found applications in solving redundancy and sequential search in relational structures. In GIS, object oriented concepts have been found useful in handling complex spatial entities and for solving problems of database modification when operations such as polygon overlay are carried out. In object oriented databases, data are defined in terms of a series of unique and discrete objects having similar phenomena such as object class having some natural structuring criteria. The characteristics of an object may be described in the database in terms of its attributes called its state, as well as a set of procedures which describe its behavior called operation or methods. These data are encapsulated within an object which is defined by a unique identifier within the database. Once the data have been encapsulated as an object in the database, the only way to change or to query them is to have sent a request known as message to carry out one of its operations. This particular slide shows the manner in which the previous example of a utility distribution system could be organized or structured by a object oriented database, wherein what will happen is it will have three objects: district, address and user, and within this it will have date informations regarding where is the district located, and it could be one of the information, or whether this district contains this particular address. Once we go to the address, then it will try to find out different types of information, that is the type of service they require, the type of building which is there, the owner, and details regarding the owner could be in terms of the name, the type of consumer he used and how much money he probably spends. So, the type of querying possible depends on the operations that have been used to define the objects. The response of the object to a message will depend on its state, and the same message may bring about a different reaction which when received by different objects or in a different context. This is termed as polymorphism. Data used in object oriented databases need to be clearly definable as unique entities. Given that these databases, as with their network and hierarchical counterparts, provide a very efficient structure of organizing hierarchical interrelated data, establishing the database as obviously time consuming, as the objects may be defined more explicitly and the various links need to be established. Once this is finished, the database provides a very efficient structure for querying specifically with reference to specific objects. Having looked at the structure of each of these databases, now comes the question, the selection. It should be apparent that the four basic database structures, hierarchical, network, object oriented and relational, all have something to offer for spatial information systems. Hierarchical systems allow large databases to be divided up easily into manageable chunks, and they are inflexible for building new search plans, paths, and they may contain much redundant data. Hierarchical approach is often useful for dividing spatial data into manageable themes or into manageable areas, so that continuous seamless mapping becomes possible. Network systems contain little redundant data and provide fast, directed and inflexible links between related entities. The network approach is ideal for topologically linked vector lines and polygons. Relational systems are open, flexible and adaptable, but may suffer from large data volumes, redundancy and long search times. The relational approach is good for retrieving objects on the basis of their attributes and for creating new attributes and attribute values from a existing data set. Object oriented systems permit relations, functionality, persistence and interdependency to be built into one system at the expense of programming tools being more complex and heavier demands on the computer program. Object oriented structuring is useful when entities share attributes or interact in a special way. Consequently, it is not surprising that these techniques are often used together in spatial information systems to complement each other rather than assigning all the work to one of them. In my next session, I would like to focus my attention to spatial analysis in GIS. Thank you.